Good morning. My name is Colin, and I'm joined by Kevin in LA.
Hey, good evening. How you guys doing?
And we're both software developers at Output, a music tech company. And today we are discussing application architecture we have put together where we're continuing to build web UIs on top of C++ audio engine. So first, some acknowledgements of our colleagues. In 2020, Spencer showed the foundation of all the work we're speaking of today. In that talk, Spencer sets up a lot of the motivations for this work, including why we're doing web UIs in general. And it seems to be leading to better products in short. The development process, modern UI tooling, the ability for web UIs to reach out to cloud services, and the collaboration between design and engineering. Spencer also discusses how Output is maintaining a fork of the JUCE web browser component, and that enables communication and developer tools, and a few of the things we're speaking of today. So we're kind of picking up where that talk left off. Also, shout out to Arthur, who mentioned some of the technologies we brought into production, and that Arthur's talk from 2021 also gets into design workflow and is really interesting. So both of those talks worth checking out for sure, especially Spencer's talk will give some good context to what we're doing here. So the first product shipped with this technology is called Arcade. From Output. Arcade is Output's subscription product, which is an internet-connected plugin in the DAW that continually delivers new sound packs. And this screen is the screen of Arcade that is built using this web technology. It allows browsing of the sound and sound libraries. So please do check that out in Spencer's talk to get a deep dive into all that stuff. So it's been a couple years, and we have the opportunity to set up a new project and the opportunity to consider some of the pain points and how things have been going. So we're going to walk you through some of the architecture decisions we made on this new project and how it's been going for the past couple years. So let's get into that. What areas we've been focused on improving. So some of the pain points, many people are familiar with this kind of thing. Emergent complexity, this is kind of an application architecture concern. Large projects are evolving over a number of years, and the requirements are changing, and the app grows. And sometimes we see bugs due to the complexity of components interacting. Sometimes we call this spooky action at a distance, meaning it's kind of like unforeseen complexity, all this components interacting. And sometimes architectures like model view controller and mediator are hard to enforce with tooling. For example, one might need strict rules about what are the responsibilities of a controller and how do you enforce that. And similarly, something like the mediator pattern where there's lots of messages being sent can be hard to trace where the messages are coming from, who's receiving them, all that kind of thing. Another category here is the protocol layer. So this is our term for the communication between the WebView and the C++ app. In particular, untyped messages we found is a substantial pain point, meaning in the code base, we can send JSON messages, and that's great, but what about like data types for those objects? Inevitably, if they're untyped, they end up getting passed around as untyped objects. Leads to bugs, code that's difficult to reason about. Imagine a message changes in the C++ side, and now it needs to be updated in the web view, all that kind of thing. And another big category here is the messaging infrastructure itself. We were able to send strings, but what about transactional messages like a request response? What about sending binary blobs like a waveform data or a file? And we'll get into this in more detail. Let's just take a look at the tech stack. The work we're presenting today is focused around how we're using this tech stack And this tech stack hasn't really changed since 2020. So again, that talk from Spencer really gets into a lot of it. But we have a C++ application written in JUCE with the app and audio engine. And then inside is the web browser component, which is actually a fork of the JUCE web browser component that runs the web app. And it's important to recall, for anyone not familiar with the web browser component, that uses the Edge and Safari provided web views. So from the operating system. So it's unlike Electron, which ships the whole Chromium stack. It uses the OS provided web view. One important note here is that the UI code we're writing is fully in TypeScript now. This has numerous benefits. This audience is probably well versed in the benefits of type safety, and hopefully allows a little more natural experience for C++ developers. Yeah, so at output, TypeScript is the de facto standard now. And on the left, we have two communication channels. We'll get into a little bit. There's what we call a direct communication, which is kind of where we started, that shipped with Arcade. You could send strings. And then we added this intercepted HTTP request, and we'll get into that a little bit more too. So now I'll hand it off to Kevin to talk about the application architecture a bit more.
Cool, yeah. So, yeah, just going through some classical architecture here, MVC. And yes, this is sort of the classic model view controller we all know and love. And on paper, it offers good separation of concerns. The controller can transform data from the model on behalf of the view. Controller can set data on the model. And the model and the view are disconnected. They're not concerned with each other. Unfortunately, over time, we kind of see these desire paths form where people just kind of want to glue the view and the model together over time, and or you'll get all of the application logic winding up in a single file for the view controller. It's a sort of a common anti-pattern that you'll find in iOS apps. And then, as your application scales over time, you start, repeating this pattern, and it just becomes very difficult to reason about model view controller at scale. You get these multiple interconnected controllers and views, and it's really difficult to enforce best practices on a traditional MVC code base. So we kind of realized that was one of the issues that we was maybe underlying some of the struggles that we had in the past. And so a lot of people in the team had experience with unidirectional data flow. So we wanted to look into that and try to adopt it. So it's inspired by Redux, and since we have a strong contingent of TypeScript engineers at Output, we'd heard how great it was. So we did adopt the unidirectional data model called Flux. Basically, the data always flows in one direction. Nothing can change the data model without dispatching an action to the store. The view itself is meant to be a stateless, sort of deterministic rendition of the current state of the store, and that's kind of core to this whole architecture. A view, when the user interacts with it, can dispatch actions, and then those actions go to the dispatcher, which applies the business logic and then produces a new updated state, essentially. From there, the state change notifies that it should be redrawn, and you get the next view, essentially. So we're kind of going to go through this fast, but here's a basic code example. So on the left, we have a sort of a trivial example here, but we want to increment a counter. And so we dispatch this action, and then on the right side is what we call a reducer. This is a function that takes in the current state and then takes in the action. And so this kind of differentiates it from other architectures where you might have a command that says update the counter to 7, because that's what the view thinks that the current state is. But when you have multiple views and multiple threads and multiple processes all trying to operate on one state, this can get a bit chaotic. So The reducer takes in the current state and then just basically an instruction of what is being attempted to do. So we can just increment the value by 1 here. And something important to note is that by definition, reducers are pure functions. So they're not meant to have side effects. Basically, it only takes in the state and the action, and it only produces 1 resulting state. So that's another bonus, basically. Reducers are pure functions, like I was saying. They define all state and state changes, and that kind of makes them easy to test. That's a huge benefit of them. You can just have your reducer and unit test it, and it's fairly straightforward. Then another component are the views, which again are deterministic. Given a state, the view always renders itself the same way. View is not concerned about any sort of business logic at all, because the view must dispatch actions to change the state. So one of the things that we liked about this model so far is that it's pretty easy to see in code review if somebody is kind of going against the grain, submitting a pull request that has, a bit of state saved somewhere that's not in the main model or has a side effect, something. So that's been a big benefit to keep people on the rails. And one side effect that we weren't expecting is that actions are a convenient wire format. That is how you can serialize an instruction to another part of the program. So in this case, it's just a JSON object. So see how that works. So in 2023, we have kind of elaborated on the existing output architecture. And if you'll recall from the previous slide, on the left, we have the view, which has basically been taken over by the web UI. And then on the right, we have the C++ application, which is hosting the store and the dispatcher. So as it turns out, though, we've also, the UI is sufficiently complex that it itself is also modeled with the Flux pattern. So when the user takes an action on the store, we can sort of see, like, is this action affecting the C++ engine, or is it a view only operation like selection or dragging some UI element or something like that? So the view can determine where it wants to dispatch things, and we'll get into some more of that flow. And as a little sneak peek, the audio engine is also just another view. It can take an entire copy of the state and render the same buffer for any given set of state. And yeah, so we'll get into some of that as well. So to start off, the view sends this action and it's serialized and sent down to the dispatcher. And until the C++ application returns the new state, the view doesn't do any changing. So we'll hand it back to Colin to get into some of how we are actually transmitting data back and forth.
Okay. Yeah, so one area of detail we're going to get into is the communication infrastructure between the C++ and the web UI. So let's chat about how this works in detail for a moment. I mentioned these two communication channels. We'll dig into this one. This is the same way that the WebView and C++ app have communicated since the arcade browser was first shipped, as I mentioned before. Essentially, strings are sent between the C++ and the web UI. That's all there is to it, really. But yeah, so in our application code, we have calls that look like this, of course, but let's look a little bit deeper into the infrastructure at a lower level. So in the web UI, it's actually setting up functions like this. In the top, you could see a function set up to receive a message, and below that, it's calling this window.webkit post message to send a message. Web devs will instinctively notice this like window dot syntax is controversial. Window is this like global object, and you're mucking around with it. It's generally considered bad practice. In this case, it's a convenient way to like inject these methods so the C++ side can send message to the web UI. So window.receiveMessage effectively is a function that is called from the C++ side. So let's look a little bit at how that works. So now we're into the native code on Mac. On Windows it looks different, but it's effectively doing the same thing. So on the top, there are these WK user content controller. This is API the Safari WebView has to handle a message that's been sent from the WebView. And on the bottom, this evaluate JavaScript call. You can see that window.receiveMessage in here. Actually, what it's doing is sending an entire string and asking the WebView to interpret it, within the runtime of the JavaScript engine, which is, it works actually. Yes, but the main point here is that we're sending strings. Okay, so we're going to get into a little bit about how we've developed this over the past couple of years. So we call that direct messaging, and we could send JSON. You could send strings, which means we could send JSON. So that's really great. It's the foundation, as I mentioned before. And one big challenge here is that the messages are all implicitly typed. So imagine a message coming in. How do we know what properties it has, et cetera, et cetera? That's a classic distributed systems problem. We need like a common protocol here for these two processes. But on top of that, what about the developer experience? As I mentioned before, untyped messages, issues arise with that. Okay, so first let's discuss the distributed systems part. Just to get our bases covered here. In order to make this work, we need a standard format for sending messages. So all messages are the same. This is how we're doing it. A message can have a name and a payload. You can see here a name is a fixed set of possibilities, and then once the name is known, now the payload can be known. So pretty straightforward. When a message is received, look at the name, and now you know what kind of message it is. We know how to parse the payload. Okay, so let's go on. So in order to have data types for these, there's kind of two parts of that. One is the data type itself, but the other is the message parsing code. And as I mentioned before, it's kind of a pain point to maintain all this by hand. So it turns out all this can kind of be automated, and I'll show you guys how we've done that. So we have code generation infrastructure where the data types are defined in schema files. And from that, the data types and the message parsing code is auto-generated, and that happens on the TypeScript side and the C++ side. The tools we're using, I'll go back one. QuickType and Loman JSON is an awesome C++ library that kind of comes with QuickType. And yeah, so again, we just update these JSON files and then run a command, and then the auto-generated code is produced. Okay, so yeah, let's look at the example. So I'm glossing over a little bit of detail here, but this is the important part. On the left, we have a user proficiency. So imagine this is how the user feels like they are at music. So it's like an onboarding survey or something. They're starting the product up, like, are you an expert? That kind of thing. And so on the right, there's some other info about the user. I don't think output actually captures their age, but I wanted to get a number in there. The point is we have all the data types we need. We could express decimals and stuff, and the data types can reference each other. So you can see the user at the bottom has a proficiency. So we're looking at the code that we will write by hand. So we'll maintain this by hand. And now this is generated TypeScript. So on the left, you see an enum, the structure. This is how you define types in TypeScript. So this will be auto-generated for us. And this is kind of all you need in TypeScript, actually. If you go one more, we'll see that, that actually how this is used in TypeScript might look something like this, where it's just kind of like typecasting. And it's just the nature of TypeScript. There's actually nothing really to do. It just is like typecasting it. And this is kind of an aside, but there's no like data validation here, and that's because on the sending side, if C++ is sending this message, that code that where it's sending that message is also auto-generated. So there's no way a software developer can like mess up the structure of a message. Okay. So on the C++ side, similar thing. We had an int, enum, and user info structure is generated for us, and some message parsing code. You can see this to JSON from JSON objects. Here we do need to do a little bit more work, but again, this is all auto-generated code. This kind of comes for free with the QuickType tool, and this j.at syntax, it comes from that Loman JSON library. It's very nice. Probably not as nice if you need to write it all yourself. And we've also added some customizations. So here's one of them, a factory method that creates a test fixture with all these values as defaults. So imagine we're writing a test. On the right here, this test wants a user info object, but it doesn't care what's in there, so it's fine with all the default values. The second test wants a user info object, but it wants an expert because that is important for the test or something. This is valuable, very valuable, because imagine the user info object changes now, and all the tests break because they had generated the user info object with the other, with the previous fields. It doesn't include the new value, that kind of thing. So our objects get updated, these test fixtures get updated, and all the tests don't break. They keep working because now they're just using the more default values. Of course, it doesn't protect against the test itself needing to be updated because you guys get what I mean. Yeah.
Yeah, well, thanks for that, Colin. So now that we have all this awesome auto-generated code, how do we actually get something done with this architecture? So I was sort of alluding to this earlier, but Colin just showed the onboarding done message with our schema here. So let's assume that the user completed onboarding and they have selected that they are an expert. We can send that message down to the C++ side, to the dispatcher. It'll do some business logic, and the output message will be that the view state has changed. So the view, aka the entire web UI, should react to this new value. So here's the actual schema definition of the message. So this is one of the activities that our developers have to do when they want to send a new message back and forth. They define the message type as well as the payload, if any, that's needed there. And then again, the auto generator generates all these message types. And Colin was mentioning that we also modified the library here. And so we've added these sort of like messages are a basic part of QuickType, but we added this context field here. So when you indicate that this is a from GUI action, our tooling knows that this is a message that's going to be coming from the web UI to the C++ side. So how do we use that? First off, just to show the API from the TypeScript side, it's pretty succinct. Once you've created a message, you get this factory method for create onboarding done message. It, names it intuitively. And then you can just send that off through the window. We've developed good APIs for that. So it's pretty efficient from a developer point of view. So that gets placed into this magic message hook essentially. And gets headed down. So once we can kind of go through the flow here. So this on receive message callback is called. You can imagine we've hooked that up to the web view. And so the first thing we need to do is pull out the name, and that tells us the nature of the message. So what we've done here, actually, we've auto-generated this deserialized method as well that matches up the name to the strongly typed description of the message, the auto-generated one. And then the extra bonus that we were alluding to, the from GUI action, we add all of those public API messages to this STD variant that we're calling public app action. And so this is a variant that holds every type of action that the GUI can call on the backend. So it's sort of effectively a compile time enforcement of the API. One of the little bonuses here is that we can show this here. So since the Flux pattern is maybe a little less common to C++ engineers, I think it's relatively rare, frankly. We ended up using the logger library, which we do have a bibliography later if you're interested in seeing some of the tooling that we leveraged for all this. But this is a nice modern C++ library that implements a Redux style store, Flux store for the C++ side. And so you have to bind this free function, the root reducer, to the store, and that's kind of the entry point. So anytime shown on this slide where we call store.dispatch at the bottom there, that will ultimately invoke this root reducer. And so as I was mentioning, we have this STD variant of all of the actions, which then are implemented by this exhaustive visitor. So long story short, if you don't handle a new message that you've added, it's a compilation error. This is another way that we can enforce the tooling. We don't even have to look at this in pull requests because the code just wouldn't build. So essentially, we use this. It's called the overloaded pattern. You can look this up on the STD variant CPP reference page. It's kind of cool, but we use that to match up the message type to a specific function, which is the reducer function we were talking about earlier. And so in this case, it's handle onboarding done. And we can do some business logic here. This is sort of, made up. But now that we have a chosen proficiency, we say, okay, we can move this user to the create page. One thing to call out here is we are passing the model by value. And I realize that's maybe shocking to some of the C++ heads here, but we're also using another library called Immer from the same author, Juan Pedro Bolivar Puente. And this basically allows C++ objects to be copy on write. So we can make a lot of low-cost copies as we're moving around in these pure reducers. And until we actually modify the object, we're not really paying for copies. So once that returns to the store, Logger also supplies this kind of like, I guess they call them cursors or readers, depending on which part of it you read, that allows us to watch the store for changes. So in this case, on the first line, we're watching the view property of the model, and that'll get called back since we have a logger watch on it. And again, now we're jumping back into the realm of things that we can auto-generate. So we make a message that announces that the view state has changed, and we can copy the new view value onto that and send the message out. So I guess something to point out is that with QuickType, we're able to basically reuse a lot of the types in our actual data model. So copying things to the serialization layer is just a matter of simple assignment. Because all the types are either the same or implicitly convertible. And so then the message is outbound and it heads up to TypeScript land and a change takes effect. So I'm going to hand it back to Colin here to get into some of the stuff that we did for transactional messages.
Okay, yes, so as I mentioned before, we are able to send strings. We dug into that direct messaging infrastructure. And that's how the majority of the messages in the app are sent, because push messaging, as Kevin was just showing, works really well for like the state has changed. But what about something where there's a transaction, like we create a thing and then we need the thing right then. And it has a unique ID and we need to do something with it right after it's created. This is a common like database kind of style, create operation. In the direct messaging infrastructure, it would look something like this, where the thing is created and then somewhere else in the code, you're handling the message that comes back. So now it has to maintain the context of the thing was being created, or we're waiting now for the thing, the create, it doesn't work very well for this like request response style messaging. And related to this is that JSON, we can only send JSON in strings, and I'll get into how that's related in a moment. But yeah, let's just talk about HTTP requests for a moment. HTTP requests, as old as time itself. Here we could see request response are being handled together on the next line of code. So we create a thing, and then the next line of code can do something with the thing that was just created. This is very natural for a web application. In case you aren't familiar, fetch, that's a W3C standard supported in modern browsers. Nothing exotic here. Web applications can naturally fetch data this way, and using a request response style API, because HTTP is a request response protocol. So go ahead. In our app, what we are doing is intercepting HTTP requests that are sent from the web view, so that the C++ side itself can send the response without running a web server. So these, from the web view side, it thinks it's asking the server for something, but there is no server. The C++ side just intercepts the request and in-memory responds to it. And so you can see on the right here now, instead of fetching to HTTP something, it's output inc, and that's just something we made up. Actually, on Windows, I don't think it works like that, but you get the idea. It doesn't hit a server. There's no network stack involved. And these are the APIs in WK WebView, WebView 2. At the bottom there, those are references. And so WebView 2 and Safari both provide a mechanism for this. So we just have a cross-platform wrapper around it. And so it's very fast. And as a bonus, this is also the solution for fetching binary blobs. So if you want to fetch a waveform or a file or something like this, we're using the same style of API. Now in this example, you can see it's requesting some data, and at the bottom it's response.array buffer. Just for anyone who isn't familiar with that, this is another W3C standard in a web application. It's the most efficient way for working with binary data. It doesn't put the data into a JavaScript list. It's an API for it's a native API, so goes into native code that's working with the memory buffer. This is also very fast, and of course for due diligence we did compare the speed of, we tried to send binary blobs and base 64 encode into strings, all that stuff. Nothing compares with this. The C++ essentially can transfer memory directly, and then on the web view, it's using the existing mechanisms for really the most efficient ways to work with the binary data. So I'll show an example. On the C++ side, so there's other infrastructure around for handling, there's things like URLs, The C++ side doesn't have to implement a full web server. Like I mentioned, there's no networking, but it does deal with requests and response. And so, parts of it do look like a web server. So in this case, it's a request to get some waveform data. It gets the waveform data from somewhere. And there's a response object. There's a body of the response. And we'll replace output span here when we switch to C++20. The idea here is to minimize copied data as much as possible until it hits the native request API. So you can see here it's just setting up the span. It's pointing to the waveform data. And there's no serialization overhead. It's just returning that data to the native response handler. And so this is just our abstraction for a response body. And there's headers. In this case, it has to say octet stream. That signals to the web view that it's a binary blob. That's nothing special. It's just like a standard thing a web server would do. And we can, we can add any response headers we want to in this, just like a web server could. And and then the binary data appears in the web view. And then that's working great. So I'll pass it back to Kevin, talk about the audio engine.
Cool. So alluded earlier that the audio engine is just another view. So here's the reminder. Let's dig into how that works. How does data actually get to the audio engine? And similarly to the web UI, the audio engine is running on another thread, and so there are, whether or not it's in a different process, it's still sort of a distributed system. Messaging cannot be instantaneous. So let's look at that. So we can use the same logger watch mechanism that we showed before. But in this case, we're just sending the entire state to the audio engine. So anytime that the model updates, we'll just send the entire state. And again, we're using this library immer that provides copy on write. And one of the other benefits that it also provides is atomic reads. So there's really no concern about sending this copy up to the audio engine. It can read from it as much as it likes, and the main thread is free to continue mutating that. And the audio engine just is stuck looking at the old data, which for determinism works out quite well. So here's sort of how that looks like. So on the upper left, we start at the store, and the message that we just saw is placed in this outgoing queue to the audio engine. And at the top of the render block, we pull in all the events that have come from the GUI since the last tick. So this is probably, the latest state, assuming that it's changed. And so then we supply that the state to basically all the children that can make noise inside of the audio engine. And we just give them this snapshot of the state. It's all read-only. Of course, it'd be a bad idea to manipulate anything on the audio thread, since generally that can cause allocation, and specifically with immer, it does when you mutate. So anything that we have to change or update, we put it in this outbound queue that's an event back, and that gets picked up by the dispatcher. So here's kind of how that looks like. Imagine that we send this playhead moved position event, and then on the next GUI main thread tick, it'll flush all the messages out of the queue and read them, and it simply dispatches them back into the whole reducer lifecycle that we showed here. So if we go all the way back to this slide, you can see that a playhead moved event may go to the dispatcher. It'll be updated in the store, and then the web UI will get the latest update of data there. And so that's kind of the circle of life there. And I think that is about it. So we'd love to kind of go over what we opened up the talk with was sort of these pain points, and basically, so on the first bullet of emergent complexity and bugs, we found that basically the benefits of the Flux pattern kind of did what it was marketed to. It prevented weird side effects. Things were easy to test. It was easy to reason about state. Things were deterministic. Most of the bugs that we've found with this application that we're working on have been just due to coding errors or incomplete test coverage or underspec things or maybe new interactions that we hadn't predicted, but nothing that we couldn't explain out of the box, right? As far as protocol layer bugs goes, we managed to basically eliminate that entire class of bugs. QA has never come back and said, yeah, there's something weird going on. We dig into it and, it's a protocol issue. Yeah, and then, the other goals that we had were to support transactional messaging and high-speed performance, both of which we demonstrated were possible. So feeling pretty good about that. There's still some things to improve upon, so maybe we'll see you next year. But what we found is that any feature that involves both the web and the C++ side tends to involve a lot of boilerplate, which we've done our best to reduce thus far. So, we build all the messaging and whatever with our automated tooling, but you still end up writing sort of a lot of code just to get some data moving around. Another learning that we had was that if you're going to persist data, having all these generated protocol layer types is great. But the problem is once they go sit in a file and you iterate on the application for a couple of weeks or a month, sometimes those types have changed. And so persistent data should be versioned separately from the protocol, which is maybe a no-brainer, but I think we were hoping this tool would solve everything for us. And the other maybe weird thing is that we do have to support Safari and Edge as separate browser stacks. So that seems fine for now, but in the future, maybe we can unify on something. So already seen some Q&A popping up here. And so just would like to thank you for your time, and we can try to field some questions before we get out of here.
Yeah, thanks, y'all.